Okay, hello everyone, welcome back. So this is another data analysis video, and I'm still covering ANOVA, still on the subject of Factorial ANOVA. In this video, what I'll do is demonstrate how to run a 2x3 repeated measures Factorial ANOVA, and I'll use a data set that produces a significant interaction between the two independent variables. So as a quick review, remember repeated measures designs use the same participants in all levels or conditions of the independent variable. So this means that each participant contributes multiple data points, one for each level of all independent variables, and these are recorded at different time points. So the data set that I'm going to use here comes from the Andy Field textbook series, Discovering Statistics Using SPSS R. And the data relates to a made up and quite humorous example, I suppose, investigating the effects of alcohol and lighting on people's perceptions of attractiveness. So this is referred to as the beer goggles effect, and the idea being here that the more a person drinks alcohol, the lower their standards of perception and the more likely they are to rate unattractive people as attractive. So the independent variables, the IVs for this study, are lighting, which has two levels, dim lighting or bright lighting, probably to replicate what it's like being in a nightclub or something like that, and alcohol consumption, which has three levels, 0 pints of alcohol, 3 pints of alcohol, 6 pints of alcohol. And the DV, the dependent variable for the study, is attractiveness rating. This is like an aggregate score of a participant's rating of the attractiveness of pictures of faces. And I suppose this is a made-up example. Theoretically, I suppose these pictures of faces have been validated on some sort of scale, independently measuring how attractive they are meant to be. Okay, so in the following sections, what I'll do is I'll tidy up the data so it's in an appropriate format for me to do this analysis. I'll also conduct some tests of assumptions. I'll do more of these tests of sphericity because we're using repeat measures within subject design. And then I'll run a two-way repeat measures ANOVA, and we'll conduct post-hoc tests and tests of simple effects as appropriate, depending on which of the results are significant. As I've already given it away that we're going to get a significant interaction, so it's likely it's going to be simple effects that we'll be doing. So not particularly looking forward to recording this video because there's a bit of wrangling I'm going to have to do with the data to get it into the sort of format that I need it in. So you'll see in a sec when I load it up, it's currently in short and wide format, and I want to convert it to like a long and thin format to make it easier to run certain of the analyses that I want. So I'm going to import a few libraries to start with. I'm going to import pandas, numpy, scipy, the stats package from scipy, matplotlib and seaborn because we'll create a interaction plot. I'll import penguin as PG and also stats models. I think I'm going to use the ANOVA RM method from stats models to run this particular analysis. Okay, so having imported those, let's import the data. So I'm going to import it and save it as a data frame object called beer_dataframe. And I'm going to use the pandas read_CSV method, and it's saved under this name as a CSV file, beer goggles lighting RM 2x3 on my laptop. So if I run that, we can see what the header is. We can see what the different column variable names are and the first few rows of data. So as I said, this is in short wide format, and we've got two independent variables here, lighting, dim and bright, and alcohol consumption, 0 pints, 3 pints, 6 pints. So you can see each of these, dim 0, that would relate to someone who took part in dim lighting and had 0 pints of alcohol. Bright 0 would be bright lighting and 0 pints of alcohol. Dim 3 would be dim lighting, 3 pints of alcohol. Bright 3, bright lighting, 3 pints of alcohol. Dim 6, dim lighting, 6 pints of alcohol. Bright 6, bright lighting, 6 pints of alcohol. So each of these columns is actually a combination of two independent variables. So what I'm going to do is I'm going to create, what I'm going to do is actually split these. So I'm going to create a long and thin data frame, and then I'm going to split say dim0 across two columns and add it as a label. So we'll have the kind of measure that will be our attractiveness rating, and then dim0 would be, you'd have a column with relating to lighting, which would show dim, and a column relating to beer, which would show 0 pints. Okay, so I'm going to split them into what they are is two separate categorical variables. So it makes the data set more granular. Okay, so let me just read this text here. It probably says all the same thing I've just said. So the other thing to note is that it's got no participant index column, and each column contains lighting and number of pints sort of combined. So it's going to take a bit of wrangling to get this data into shape. And one approach that may work is to create a participant ID column, then convert the data to long and thin based on lighting by creating a lighting categorical variable and a rating categorical variable. After this, a pints categorical variable can be appended to the data frame to align with the correct index and lighting categories. So I'm gonna append a pints categorical variable, and then what I will do is I will rename each of the lighting just so it says dim or bright essentially, and ignores the beer, the number of beers consumed. All right, so let's run. What I'm going to do here is I'm going to create a long and thin data frame, and I'm going to create an object called categorical condition, and I'm going to use as the list our beer data frame columns for that for this object. And then when I create this new data frame called groups long, I'm going to use the pandas melt method. We're going to pass the original data frame, and the value is going to be this categorical condition variable or object, which is kind of a list essentially showing all of the column names against each kind of value. Value name will give rating, so that will be our kind of attractiveness rating, and we'll tell it to ignore the index. So if I run that and then we call this group's long object, you can see what it's done now is our actual scores are now given the label rating, and it's, I mean, not the most informative, but lighting, our variables, our IVs are now just labeled variable, and there's dim0, dim3, dim6, bright0, bright3, bright6. You can only see some of them here because it's condensed the data frame. But what I'm saying essentially is we want to split this dim and 0 pints across two separate columns, essentially two separate categorical variables. So adding a variable for pints is going to require filtering and combining multiple categories. So for example, dim0 and bright0 both mean 0 pints consumed essentially. All right, so let's look at this data frame, and what you can see is we've got 156 data, we've got 166 observations or participants, or sorry, data entries. We've not got 156 participants, we've probably got 52, and the variable, as we want it to be, this combination of two different categorical independent variables, is an object. Our rating is a float, which is the correct. We want our rating scores to be shown as a float number, a numerical value, so we need those to be a scale essentially. So what I'm going to do first is create a participant ID column on the original data frame. And I'm going to basically just use BDF, and I'm going to add something called participant ID, and it's going to basically use the index number that Python automatically adds to the data frame. And if we call the header of this, you can see we've now got a participant ID number from 0 to 25 essentially. 26, so it's going to be 26 in each, dim0, that type of thing. Right, so next thing to do is to map this participant ID variable onto this kind of new long and thin data frame that we've created here. So we've added it to this original data frame. But now we want to kind of map it onto the new long and thin version. I don't want to work with a short and wide data frame in this case. So what we're doing here is adding an identity variable for each participant to account for the structure in the data, due to the fact that each participant has contributed multiple data points. And to do that, all I'm going to do is I'm going to create a new object on groups long, called a new variable on groups long called participant, a new column essentially, and that's going to basically take the participant ID variable from the original beer data frame, and it's going to sort of map that onto our groups long data frame. You can see there, participant. We've now got our long and thin. We've still got these two independent variables combined as one. We will split them in a sec. We've got rating, and we've now got a participant ID. So we're getting closer to having a data frame that's useful. So now we've got this new data frame object containing only rating separately, but we want to split these up. What I'm going to do is create a new data frame, a completely separate data frame object containing only data points when 0 pints of beer were consumed. So that's basically going to be it's going to be a new object that contains all the ratings on the dim 0 and bright 0. Okay, essentially, and the way I'm going to do that is I'm going to create this new object called pints_0, so 0 pints drunk, and it's going to be the groups long data frame. I'm going to use the .loc method, and then in the square brackets I've passed these parameters, and notice I've had to use parentheses as well to enclose them. If you miss off the parentheses, you will get an error. And what I'm saying here is from groups long.variable. So from the variable, which is this, remember it gave it the name variable, from this feature or variable object, wherever something's equal to dim 0, exactly equal to dim 0, extract that, or this vertical bar means here is a boolean for or. Where groups long variable is exactly equal to bright 0, extract that, and we're going to save them in this new object .0. So let me run that, and what you should see is it's just extracted all of the bright 0 and dim 0 data entries essentially. So we're going to do the same thing here for 3 pints, but this time it's the same syntax as above, but this time we'll call it pints 3, and we're just going to say from variable, from the groups long variable called variable, extract everything that is labeled as dim 3 and everything that is labeled as bright 3, and save that as a new object called pints 3. So we're now, by doing this, we're basically splitting that long and thin data frame into 3 separate objects essentially. The long and thin data frame still exists as groups long because we've given them new names. Okay. Same for 6 pints. Okay, so we just extracted all those in the dim condition who drunk 6 pints, all those in the bright condition that drunk 6 pints. So now what I'm going to do is create a new label, a new object that is basically a list that contains the label pints_0 repeated 52 times, because each of these 3, and we're going to append it to these objects essentially. So each of these objects has 52 lines in it, okay, rows. Okay, so to do that, I'm going to create something called beer 0, and that's going to be pints 0, which, if you remember, is these objects we just created above, these separate kind of tables, pandas data frames, times 52. So it'll basically be a vector really, or a pandas kind of numpy array, 52 rows long, that just says pints 0, 52 on 52 different rows. So if I run that, and then what I'm going to do is append that beer 0 object to the 0.0 data frame object we created above. So this 0.0 data frame object here, this thing, I'm gonna basically put beers 0, append it here. It'll basically just say beers 0. And let's run that, see what that looks like. And it's given us an error. It's telling it doesn't like the way I've done this. Essentially, it's saying use the .log method, but it will have worked. And we're going to do the same with beers 3. So we're going to create an object called beers 3. It's going to say have the string 0.3 repeated 52 times along 52 different rows, and then we're going to append it to the 0.3 data frame object. Same with 0.6, append it to the 0.6 data frame object. So now if I call each of these data frames 0.0, we should see we've got this new variable appended. So we've got our attractiveness rating, we've got an ID number for each participant, and we've now got a variable that just records whether they had 0, 3, or 0, in this case 0 points for this particular object. But we'll do the next ones. 3 points for this particular object, 6 points for this particular object, yeah. And we've still got like the lighting. It's kind of a combination, and we want each of those. We basically want it. The next thing we will do essentially is concatenate that together. So those 3 data frame points, 0.0, 0.3, 0.6, we're going to concatenate them together column wise, essentially. Sorry, row wise is what I mean to say there, into one big data frame. And if I run that, we're calling this one beer long rather than groups long to give it a different name. So let's have a look at what that looks like now. And what you should see is it's basically stacked that, and that object on top of each other. Right. Okay, so that's useful. We're making some progress here. But what we want really is where we've got variable. We now don't need these 0s, 3s, and 6s attached to this, and having them there means that we just want where it's the lighting. We want this variable now to just we could create a new one, or we could change this in place. I'm going to change it in place. This thing called variable, and where it's dim, I don't want to say dim 0, dim 3, or dim 6, because that will give us effectively 3 separate categories. I want it to just say dim. Where it's bright, the same thing. I want it to just say bright, not bright 0, bright 3, bright 6. We don't need it to say 0, 3, or 6 because we've got this new points variable appended now. And the way I'm going to do that is just going to use this. I'm going to use the replace method essentially, because as they currently are, because it has dim 0, dim 3, dim 6, bright 0, bright 3, bright 6, they're different strings, so they're treated as different categories. And I just want to replace the 3 dim strings with just one group dim, and the 3 bright strings with just one group bright. And I use the replace method to do this, and I'm going to pass it a dictionary. So in the parentheses after replace, so hopefully you can see what I'm doing here is I'm taking the beer long data frame, the one above. I'm taking the variable that is actually called variable. I know it's not a very useful name. I could rename it, I guess. And setting that equal to beer long variable dot replace. And then in the parentheses after replace, I'm passing you can see the curly braces and these key value pairs. I'm basically passing a dictionary, a Python dictionary, saying wherever it says there's a string saying dim 0, just replace it with dim. Wherever it says dim 3, just replace it with dim. Wherever it says dim 6, just replace it with dim. Where it says bright 0, just replace it with bright. Where it says bright 3, replace it with bright. Where it says bright 6, replace it with bright. Okay, so let's run that and then look at the beer long data frame now. So that was a lot of wrangling just to get this into the format to run a repeat measures ANOVA. So we've now got our 2 independent variables where they were combined and as a single feature. They now split, so we now have it's called variable, but it relates to lighting. I won't bother changing the name. So we've now got a lighting variable called variable, which has two categories, dim and bright, and a pints variable, which has three categories, 0 pints, 3 pints, 6 pints. Okay, so that's sufficiently granular for us to run this analysis. So that was quite a bit of a complex bit of tidying and cleaning, and it took some manipulation to get the data frame into the condition that I think is best to run this two-way ANOVA we're going to do. It's worth keeping in mind, though, that much of the kind of work you do in data science when dealing with data sets from different sources, so this wasn't my data set, and certainly when you haven't collected that data yourself, it involves you spending quite a bit of time cleaning and organizing the data. Okay, so we can now, after 20 minutes of me talking and manipulating data, wrangling data, we can now run a repeated measure. We've got a data frame here, and we can run a repeated measures ANOVA. So the first thing we're going to do is do Morchley's test of sphericity. So this is a test of assumption that the variances of the differences of all possible pairs of within subject conditions are equal. So if sphericity is violated, then variance calculations may be distorted, resulting in an inflated F ratio. So if the assumption of sphericity is not violated, we can assume the data is appropriate for use with a parametric statistical test like ANOVA. I've said in previous videos, these types of statistical tests of homogeneity, of normality, things like that, tests of parametric assumptions, there are a lot of debates about the value of them, but we're going to do it here, and just so people are aware how to do it. I'm going to run Morchley's test of sphericity using the pg.sphericity method, so the Penguin software library, the sphericity method. And you can see here I'm using pg.sphericity. The data we're using is beer long, so our long and thin beer data set frame. The DV is rating. The subject is obviously, we want to know what the ID number is for each of our subjects, our participants. Is this variable we label participant, so it's just the participant's ID number. And the within subjects factors, so the independent variables for this repeat measures design. Remember, it's a factorial design, so we're passing it a list of two. The first one is lighting, which is saved as it's currently got the label variable, and the second one is pints, which is the number of pints drunk there. I can't be bothered to actually change this to the word lighting, so we'll stick with variable. So if I run that, we get this output. It gives us a Boolean sphericity equals true, so it's telling us it's true that we can assume sphericity with this data. It gives us this Morchley's omega value 0.495, chi-square value of 1.26, 2 degrees of freedom, and a p-value of 0.53. So this indicates we've not got a significant Morchley's test. And remember, the null hypothesis for this test of assumption is that we can assume sphericity, that differences of variance between the within subjects conditions are equal. All pairs of within subjects conditions are equal. If we get a significant Morchley's test of sphericity, then we can't assume that, theoretically. But here we've got a non-significant Morchley's test, so we're probably safe to assume sphericity in the data set. And we don't reject the null hypothesis of sphericity, and the variance of all possible pairs of within subject differences are likely to be equal. So we can proceed with the standard repeated measures ANOVA for our analysis. And to report Morchley's, I've seen it done different ways. There are a number of different ways that people do this. I've seen the omega value reported and not reported, the chi-square value reported and not reported. So you could, to formally report this in some sort of report, you'd say something like Morchley's test of sphericity was conducted. This showed a non-significant result, and you could put something like this: Morchley's omega equals 0.95, chi-squared 2 degrees of freedom is 1.26, p equals 0.53. So sphericity was assumed for all analysis, something like that. Okay. All right. So with that, we're kind of assuming sphericity with the data. So it can just conduct a kind of bog standard repeated measures ANOVA. There are a number of ways in which you can run that type of analysis using Python. I'm going to use the Penguin RM underscore ANOVA method rather than fitting the formula using stats models. Okay, so I said I might use stats models. I think I imported the RM ANOVA version from stats models at the start, but what we'll do is I'll use the Penguin method. So okay, so the parameters for this, so I'm going to create this new object called res for results. And I'm going to set that equal to penguin.rm underscore ANOVA, and you can see the different parameters that it takes and the arguments that I've passed to it. So the data is the beer long data frame, the DV is the rating, the attractiveness rating. Our within subject factors are the lighting variable called variable and the pints variable. Our subject ID is the participant variable column, and as for detailed equals true. That returns the result as kind of a pandas data frame, which is nicer to look at. Note the difference here to one-way repeat measures ANOVA. I think I demonstrated how to do RM ANOVA using Penguin, and we just passed one, the name of one variable, but here we pass a list of both within subjects independent variables to the within parameter. So let's run that and see what results we get. Okay, so here, so we've got 3 lines of output. The first one shows the main effective variable or lighting in this case. The second one shows the main effective pints or number of pints drunk. And the third one, variable times pints, it shows the interaction effect for both independent variables. So we've got 3 hypotheses really we're testing. Is there an effect of lighting? Is there an effect of beer? Is there an interaction between beer and lighting? So let's look at our results. So we've got an F value for lighting of 40.70 if we round that to 2 decimal places, and an uncorrected p-value of 1.117479 times e to the negative 0.06. Okay, so a very, very small p-value. So what we would have to do here is move this decimal place 6 places to the left to get the actual p-value. It's presented here as scientific notation for us here. We're using the uncorrected p-value rather than the greenhouse geyser because we're assuming sphericity. Okay, if we weren't able to assume sphericity, then we'd use this corrected greenhouse geyser p-value. So we've got a significant main effect of lighting. Pints, we've got an F value of 97.22. and p is 5.885168 times e to the negative 18, so a very, very small p-value. Okay, so we've got a significant main effect of pints. And then if we look at variable times pints, so the interaction, we've got an F value of 19.76 and a p-value of 4.735080 times e to the negative 0.7. So again, a very, very small p-value. So what we're seeing here essentially is we have a significant ANOVA model. We can see there's a significant main effect of lighting, and we have a significant main effect of pints and a significant interaction between lighting and beer. So the significant main effect of lighting, we would kind of form the report list. We'd say I've put it in parentheses. You could do that in some sort of report you were writing. But I've put F, then I've opened the brackets and put the between and within subjects, or the between and error residual degrees of freedom. So you can see that's 1 and 25 in this case. So luckily, quite nicely, it gives you them as separate columns. Degrees of freedom 1, degrees of freedom 2. So for lighting, we've got F, open brackets, 1 and 25 degrees of freedom. Then we're closing those parentheses, equals 40.70 if we round that to 2. Comma p is less than 0.001, so that's as precise as I've bothered to state the p-value for that one. Same for the other. Significant main effect of pints, so F, comma 2, parentheses 2, comma 50, so 2 and 50 equals 97.22, p is less than 0.01, and the same for the interaction. A significant interaction, F, parentheses 2, comma 50, 250 equals 19.76, P is less than 0.001. So although we have significant main effects, the fact that we have a significant interaction tells us that the main effects are not likely to be consistent across all levels of one of the independent variables when it's in interaction with the other. So something's different happening at different levels of the independent variable, depending on the level of the other independent variable. So a sensible way to proceed is to obtain an interaction plot for the means across all interaction groups, and some means for each group, and then we could, so let's get an interaction point plot, and then what we would do is to to pick apart what is going on with this interaction. We then do some simple effects comparisons. Okay, so let's create an interaction plot to visualize the differences between groups. So I'm going to use the Seaborn point plot, so SNS.point plot, pass in the data, which is our beer-long data. Our x variable, the variable we're going to put on the x-axis, is pints, because we've got 3 levels for that. So when you're creating these types of interaction plots, I recommend you, whichever independent variable has the most levels, plot that, the most number of groups, plot that on the x-axis. Our y value is going to be the rating, that's our scale rating, attractiveness rating. And then the different colors for the lines, which we're specifying with the hue parameter, we're going to use are the variable, lighting variable, essentially, because there's only 2 levels for that, dim and bright, essentially. Okay, I specified dodge equals true, so it doesn't just stack points on top of each other. And if I run this, there we go. That kind of makes it easier. So we've got this significant interaction, and it makes it easy for us to immediately see what is going on. So the blue line represents the dim lighting condition. The orange represents the bright lighting condition. Data points here are 0 points, here 3 points, here 6 points. So these are the group means for our data split by pints and split by lighting, essentially. And you can see there, in the 0 points condition, there doesn't seem to, there's huge overlap in the error bars, so there's not going to be a significant difference between dim and bright lighting when someone's not had any drink. But if we compare these two and these two, they're likely to be different. Same if we just look at the blue line and compare 0 and 3, they're likely to be different. Blue line compare 3 and 6, likely to be different. And the same with the orange line, comparing those. Or even if we looked at dim and 0 compared to bright and 3, they're looking like they will be different. So lots of different pairwise comparisons we could make there. So we can see attractiveness ratings if we look at, I'm just going to read the text that I've put underneath. We see they were higher in the dim lighting condition compared to the bright lighting condition. So the blue line is kind of generally higher than the orange line, but not consistently. And this is where our interaction is going to come in. So when people, it's definitely true when people have drunk 3 or 6 pints, but not when they drunk 0 pints, where the group means are kind of very similar and probably the same if you sampled again, or about the same. So considering the dim lighting condition in isolation, just the blue line, we can see that attractiveness ratings were higher in the 3 pints condition compared to 0 condition, higher in the 6 pints condition compared to both 3 and 0 pints condition. Similarly, when we just look at the bright condition, the orange line, we can see that attractiveness ratings were higher when 3 pints were drunk compared to 0 pints. And for 6 pints, there are higher attractiveness ratings were higher compared to both 0 and 3. Okay, so where the error bars don't overlap is a strong indication that those will be statistically significantly different. However, to confirm this, what we would want to do is get a table of descriptive stats and conduct some tests of simple effects using some type of p-value adjustment to control for type 1 errors. Okay, so I'm going to create an object that represents all combinations of groups in the interaction. Okay, so that's going to give us dim and 0. Effectively, what I'm doing here is creating an object that replaces the one we got rid of and split apart at the start with all the data wrangling. I'm going to call it interaction groups. And you can see here it's going to consist of lighting plus one of the beer type of strings. So it'd be kind of lighting, dim and pints 0, lighting, dim and pints 3, lighting, dim and pints 6, lighting, bright and pints 0, and so on. So hopefully there we go, you can see what that looks like now. Okay, so having done that, I'm going to append that to the to the beer long. I'm going to give it a variable name of interaction group, _group, and I'm going to append that to our data frame. So effectively, what this interaction group variable is pretty much that original variable that we had to split up across lighting and pints. So maybe it would have been easier if I'd, rather than change this in place, if I'd have just created a new variable and we could have then used this instead of creating our interaction groups. We could have used that to obtain descriptives, as I'm going to do here. So to obtain descriptives by interaction group for comparison, I'm going to create a new object for each of the interaction groups essentially, and that object is basically just going to extract the kind of rating score for each entry where the variables say dim and pints 0, and likewise, so dim pints 3 I'm using the dot load method to do this, and it's going to extract the rating scores here where the variable's dim and the pints 3, so on and so forth. Let's run that, and then I'm going to just use print some f strings that will give us, they'll print out for each of these objects we've created, and then what I'm doing then is passing them into this f string and saying for that object give us the mean, return the mean, so dot mean to 2 decimal places. So there you can see. So we can see what the mean rating was for dim and 0 pints. It was 35, dim and 3 pints, 62, dim and 6 pints, 78. So a general trend of increasing ratings with more beers, essentially, with more alcohol. So with that done, it makes it easier really to, so these values represent these 6 group means essentially. And what we can now do is conduct some tests of simple effects. And I'm going to do this, what I'm going to do to conduct these follow-up tests of simple effects, I'm going to use the pairwise _test methods from Penguin. And I'm going to ask it to use a Bonferroni correction to adjust the p-value. And you specify that using the p-adjust method. So you can see here I've got p-adjust equals Bonferroni. Okay, so the syntax in this cell here, I'm creating an object called simple effects, which is just our output of a table, which is going to return a table essentially with our pairwise test. It's going to compare all combinations of these. So it's going to compare these 2 points, 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 same for the blue, and then it will compare this one with that one and this one with that one, that type of thing. So it'll return quite a lot of results. It'll look a bit messy, I guess, and then we can look through and interpret them. So what I'm doing is create an object called simple effects. I'm using Penguin pg.pairwise tests, saying data is beer long, the dv is rating, within is our interaction groups object that we created above. This one, our variable that we appended above, intergroup. And the subject, we're using our subject ID, specify that's the participant variable, Bonferroni adjustment. And here I'm calling this new object. So we can see the output, simple _f, and I'm using .round3. So I'm basically saying round everything to 3 decimal places. So it's kind of looks a bit tidier. All right, okay, so it's what that is a messy table. 15 comparisons in total, based on how many levels we've got for our 2x3 ANOVA. So I'm not going to go through and I'm not going to go through and sort of interpret each of these in turn, but what you can, but I'll do a couple, and then it's easier. A lot of them are statistically significant, and we kind of knew that was likely to be the case because we could see a lot of these group means that the error bars do not overlap. The ones that do are these two, so dim and bright when people have had 0 pints, and another one that does is likely to be this one and this one. You see the error bars overlap between dim and 3 pints and bright and 6 pints. Yeah. Okay. So, but the others, unsurprisingly, all seem to be statistically significant. So if we look here, basically the first comparison we're looking at the bright 0 pints condition to see if it's significantly different from the bright 3 pints condition. We've got a t-value of -3.72. If we round that, when you report this, you can ignore the negative sign. It's just a function of which group mean was subtracted from which other group mean when the t-test was conducted. We're going to use the corrected p-value, and it tells us the p-value is 0.015. Okay. Because we are making multiple comparisons, and we're going to use the Bonferroni adjusted p-value, not the uncorrected p-value. And what we can see is that it is statistically significant. So it's statistically significant difference between bright and 0 pints and bright and 3 pints. So what that's telling us, if we look at our means, so bright 0 and bright 3. So bright 0 has a mean of 38.42, bright 3 a mean of 49.23. It's telling us that bright 3 had a significantly higher mean attractiveness rating than bright 0. Okay, those conditions essentially. So the two that are not significant though that we will look at are bright and 0 pints and dim and 0 pints, and we can see we've got a t-value of 1.22. and the corrected p-value is given as 1. It's not going to be exactly 1, but that's a function of the fact that I asked it to round to 3 decimal places. It would have given us a more precise p-value, but it's not statistically significantly different, and we kind of knew that. So it's dim 0 has a mean of 35, bright 0 has a mean of 38.42. So one's slightly higher than the other, but they're not significantly different. We knew that just looking at this, didn't we? Essentially, they're not. They overlap significantly. Okay, so that's one of the false ones. And the other one here is bright and 6 pints, dim and 3 pints. We get a t-value of 1.29. And again, it's given the p-value as exactly 1. It's not that. But so that was, let me look again, bright and 6, dim and 3. So if we look at these, bright and 6, 59.23, dim and 3, 62.77. It's telling us that those two means are not significantly different. Those were the ones where I kind of pointed out this and this overlap error bars are not significantly different. Okay, so that's quite a thorough set of pairwise comparisons using a Bonferroni correction. So we can see most of these are statistically significant differences. The only groups that are bright 0 and dim 0. And that makes sense as they're very similar if you look at the interaction plot and the descriptives. Bright 6 compared to dim 3 also. If you look at that, you can see the error bars overlap. The full risk, I'm not going to read these out because that'd be very boring and make this video even longer than it is. But you could write, if you wanted to formally report all these results, you could kind of probably put them in a table, but you could specify them here. I've specified the mean for each group compared to the other group mean and whether it's a statistically significant difference or not. All right, so So the results seem to, as a whole, they seem to indicate that the amount of alcohol consumed influenced participants' ratings of attractiveness, with higher ratings being associated with higher levels of alcohol consumed. Okay, lighting seemed to influence rating interaction with alcohol, with those rating faces in dim lighting giving higher attractiveness ratings than those rating faces in brighter lighting. So the blue line was higher than the orange line. However, that difference between the lighting conditions wasn't consistent, as it didn't occur when participants had not consumed any alcohol. So that will be what is driving the significant interaction, essentially, is that these are generally dim lighting, higher attractiveness, more alcohol, higher attractiveness rating. But when people had not drunk any alcohol, there was no significant difference between the two. All right. That was a very long video, and part of the reason why is because I did quite a lot of wrangling of the data to start with to get it into a condition to run these tests. So what we've done here is put the data in a long and thin format. We've had to split two independent variables that were saved as with one label, split that across two categories, two different variables, two different features. We've then done Morchley's test of sphericity. We've done a repeat measures ANOVA using Penguin, and then we've done some pairwise comparison tests with Bonferroni adjustment to investigate the significant interaction between the two independent variables. Hopefully that was helpful. The next video I'm gonna explain. I'm going to demonstrate and talk about mixed factorial ANOVA. So where we have two independent variables, one that's independent groups, one that's repeated measures. So slightly more complex design. And then that will be pretty much it with regards to ANOVA. I've made quite a lot of videos on ANOVA now, it's probably more than 10. And it'll be good to move on to something else. I think I will make some regression videos next. So thanks for listening. I hope it was helpful.